This is video 3 for the series and parallel unit. In this one, we're going to talk about Kerkhoff's second law. Now, this one deals with circuits that have parallel resistors, or we can think of branching wires. So remember, one of your learning goals is the ability to tell the difference between series and parallel. Okay, Kerkhoff's second law tells us that the sum of all currents equals 0. Now, this is only true at a junction. So this isn't saying that the sum of all currents for an entire circuit is 0. It's the sum of all currents at a junction should equal 0. And again, this allows us to study how currents are affected by circuits with branching that branches off in different directions. All right, so let's take a look at this this circuit here. We got our power supply, so that means we have a main current coming off of it. Now, when a current encounters a junction like this, sometimes junctions are called nodes, it will split. Some of the current will go one way, and the other current will go the other. So since this one's going through R1, I'm going to call this current I1, and this current is going to go through resistor I2, or R2, so I'm going to call it I2. And once again, we consider these negative compared to the first one, so I can say that I minus I1 minus I2 equals 0, or I equals I1 plus I2. And notice that once these currents go through their respective circuits, they will recombine to form that main current and return to the battery. And this is because of conservation of charge. The charge cannot be created or destroyed, so what leaves the battery must enter it. So that's our currents. We can also think about having a voltage drop, like a delta V1 across this resistor, and a delta V2 across that resistor. You may remember, though, that when we did some early experiments in the virtual lab, that when we saw a configuration like this with parallel resistors, that delta V1 was the same thing as delta V2. So for the time being, I'm just going to call it VP, delta VP for parallel. So once we have this, we can go ahead and apply Ohm's law. Current equals voltage divided by resistance. So I could see that for the main current I, it's going to be the EMF divided by the equivalent resistance, and I1 would be like that delta V1 divided by R1, and I2 would be that delta V2 divided by R2. And in this particular circuit, all the voltages are the same, so they would all cancel out. And what I'm left with is that 1 divided by the equivalent resistance would equal 1 divided by R1 plus 1 divided by R2. So again, what makes the circuit cool is that the voltage drops across each of these resistors or circuits, it's the same as the power supply. And then this gives us a way also of calculating the equivalent resistance. So this time the equivalent resistance equals the sum of 1 divided by each individual resistor. But we also have to remember to flip it back over, because it's 1 divided by Req equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R whatever. Once again, we can find the main current. And then once again, we can use each resistor to calculate the currents through each wire and the voltage drop across each resistor. So here we have an example. I've got a 12-volt power supply. I'll write this out to make it a little bit bigger. This first resistor, R1, is 6 ohms, and the second resistor, R2, is 12 ohms. So once again, I'm going to make a little table to keep track of everything. So I have my R1, which is 6 ohms. I've got my R2, which is 12 ohms. And then I have like my totals. So my total, so that means I got my REQ. All right, let's go ahead and get to it then. The equivalent resistance is the sum of 1 over each individual resistor. I have to invert it. So that means that the equivalent resistance equals 1 divided by 6 plus 1 divided by 12. And I need to flip that. So 1 over 6, that's the same thing as 2 over 12. So I got 2 twelfths plus 1 twelfth. So that would be the same thing as 3 twelfths. But then I have to flip that. So that'd be the same thing as 12 divided by 3, which equals 4 ohms. So the equivalent resistance of this circuit is 4 ohms. That's something else that's special about these branching circuits. The equivalent resistance will always be less than your smallest resistor. Notice that 4 ohms is less than 6. That is always true. The purpose of branching circuits is to reduce the overall resistance of your circuit. All right, our main current then would equal the EMF divided by the equivalent resistance. That's just going to be 12 volts divided by 4 ohms. That's pretty simple. 3 amps. So it's going to go down here. This time I cannot say that every current is 3 amps. However, what I can say is that the voltage, the voltage of my power supply is 12 volts. What I can say is that the voltage drop across each resistor would be 12 volts. It'd be the same as the power supply. So then to find the current, current is voltage divided by resistance. So what I could do is I could take the volts and divide it by the resistance. So 12 divided by 6 is 2 amps, and then 12 divided by 12 ohms is 1 amp. And notice that I have 2 plus 1 equals 3. Power is current times voltage. So I have 2 times 12. That gives me 24 watts. And then 1 times 12 gives me 12 watts. And then if I add these together, I get 36 watts. If I did the power supply times the main current, I would get the same thing. I would get 12 times 3, which is 36 as well. This also means that each resistor needs to handle 12 and 24 watts. That is a lot. All right, this concludes video 3.